Hello, my name is Alex Odenkirk, and today I'm going to be showing you how to use the method of undetermined coefficients to solve second-order linear differential equations. Now, the method of undetermined coefficients is used to specifically solve non-homogeneous second-order linear differential equations, which come in the basic form y double prime plus some function p of t times y prime plus q of t times y is equal to g of t. Now, you're not able to use the method of undetermined coefficients on all second-order linear non-homogeneous ordinary differential equations. There's certain conditions have to be met to make sure you're able to use it and that it will give you an answer. So first of all, you have to have second-order linear non-homogeneous differential equations that have constant coefficients. So we saw the form above where the first derivative and the function y itself, the first derivative of y and the function y itself were multiplied by these functions like p of t. Well, in this case, we need those functions to be constant. So for example, if our function was a y double prime plus b y prime plus c of y is equal to g of t, then we would need a, b, and c to all be constants in order to use the method of undetermined coefficients. And secondly, we need to make sure that our function g of t, our non-homogeneous term, as we'll refer to it for the rest of this presentation, has to be one of three basic types of functions. It has to be a polynomial function, an exponential function, or a trig function, a sine or cosine function, or some combination of those three different types of functions. Otherwise, you're not going to be able to make an accurate guess, and you're not going to be able to solve the differential equation. So basically what this function involves is making a guess for what we think that function y is. And we then take the first and second derivatives of it and plug it back into our original ordinary differential equation. We simplify it and solve it out and try to find the coefficients that went along with our guess. And if we're able to solve for those coefficients, then we know that our guess was correct and that we found a particular solution to the function, which we'll talk about in a minute. So if we aren't able to find any coefficients, then we know our guess was incorrect and we have to go back and re-guess or make sure that our function fits the criteria to use the method of undetermined coefficients. So here we have a table that shows us kind of our suggested guesses for each type of basic function. So for example, if our non-homogeneous term, our g of t function that was on the right side in those second-order linear differential equations we were looking at earlier, were an exponential of the form little a times e to the ct, where little a and c are both constants, then our guess, which is our guess for y, our guess for our particular solution, should be big A, which is just an unknown coefficient, times e to the ct, where c is the same coefficient as is in our non-homogeneous term. And then you can see if we have a polynomial function, our guess should be a polynomial of the same degree, just with unknown coefficients. And if our non-homogeneous term is a trig function, a sine or a cosine function, or some addition of the two, then our guess should be the addition of a sine and cosine function with unknown coefficients. So let's try an example here. Let's say we have the basic system y double prime minus 4y prime minus 12y is equal to 3e to the 5t. Does this meet our criteria to use the method of undetermined coefficients? Well, we can see that we do have constant coefficients on the left side. Right? We see that our coefficient for the first derivative of y is -4, and the coefficient of y is -12. So we meet that criteria, and then we see that we have an exponential function on the right side, so we know that we meet that criteria as well. So if we want to find the solution to this system, what we're looking for really is the general solution, which is the solution to the whole second-order linear differential equation. And when we have a non-homogeneous second-order linear differential equation, we need two parts to find the general solution. We find the homogeneous solution to the system, which means replacing the non-homogeneous term with 0 and then solving. And then we need a particular solution, to the system, which we will find using the method of undetermined coefficients. We add these two solutions together, and we get the general solution. Now, first of all, to find this homogeneous solution, which we're going to assume for the sake of this discussion that you already know how to do, potentially using, say, like method of characteristics or something of that nature, which is what we'll use here. If you don't know how to do that, there are plenty of other videos and tutorials on different sites on how to use that. But if you're looking, so if you need to find this homogeneous solution, what we're going to do is we're going to replace our non-homogeneous term, that's our 3e to the 5t, with 0, making this system homogeneous. And then we find a characteristic equation. So we turn our y double prime minus 4y prime minus 12y into r squared minus 4r minus 12 using the method of characteristics. Now we chose this function because it's nice and easy, and it simplifies into this pretty little system where we get r minus 6 times r plus 2 is equal to 0 once we factor it out. So that makes it pretty easy to just say that r1 is equal to 6 and r2 is equal to negative 2. Now that we've found those r's, we can plug them into our general solution for a homogeneous second-order linear differential equation to see that our homogeneous solution is some constant c1 times e to the 6t plus some constant c2 times e to the negative 2t. So now we have our homogeneous solution. All we need to get the general solution to the whole system is the a particular solution. So we're going to look at our table of guesses here. Now we see that our non-homogeneous term, our 3e to the 5t, is an exponential term, right? Where little a is equal to 3 and c is equal to 5. So we can see using our table of guesses that the form of our particular solution of our guess for y should be big A times e to the 5t, right? Where c is equal to 5. So our guess for the particular solution is a times e to the 5t. Now we need to find the first and second derivatives of our particular solution so we can plug it back into the original system and solve for a, right? So the first derivative of our y particular is 5a times e to the 5t, and our second derivative is 25a times e to the 5t. So we plug these into our original differential equation. We plug in our values for y, y prime, and y double prime. And we get this system here, which we then solve and simplify out, multiply everything together and add to get negative 7a times e to the 5t is equal to 3e to the 5t. We divide both sides by e to the 5t to get negative 7a is equal to 3. We divide over our negative 7, and we end up with a is equal to negative 3 over 7. Now, since we found a value for a, we're pretty sure that our guess is correct. And all we have to do to check that is to plug it back in to our original function. If we did that, we would see that our guess is correct, that everything solves out. We get the left side equal to 3e to the 5t, and the right side is equal to 3e to the 5t. We know that our guess was correct. So that means our final particular solution is y particular of t is equal to negative 3/7 e to the 5t. That means our total general solution, which again is the particular solution added to the homogeneous solution, is going to be c1 e to the 6t plus c2 e to the negative 2t minus 3/7 e to the 5t. That's our general solution. So now we're going to try a different one. We're going to see what happens when our non-homogeneous term g of t is equal to a polynomial function. In this case, a third degree polynomial function, 2t cubed minus t plus 3. And to make things easier, we're going to keep our original function on the left side, y double prime minus 4y prime minus 12y, because we already know the homogeneous solution to it. So all we need to do is find the particular solution to it. Right? So, as I mentioned before, note that g of t is a polynomial of degree 3, which is important when we're making our guess, because when we look at our table here, we see if we have degree 3 in our polynomial, we need to guess, our guess also needs to be a polynomial of degree 3 with these unknown coefficients. And it's very important, even though our original function doesn't have a t squared term in it, our guess should always still have every single term in it. It should still contain a t squared term. right? So that means our guess is going to be, for y particular, is some coefficient a, t cubed, plus a coefficient b, t squared, plus ct, plus d. So just like before, we need to take the first and second derivatives of our particular solution, and we get first derivative is 3at squared plus 2bt plus c, and our second derivative is 6at plus 2b. Just like before, we plug these into our original equation, and we get this whole ugly mess, which we can sort of simplify just a little bit to get this, where you can see we have it so the coefficient of each t term is displayed separately. And now what we do is we set the coefficient of each t term on the left equal to its corresponding coefficient on the right, and solve for our unknown coefficients. I know that's a little confusing, but here's our example. We can see on the left side the coefficient of t cubed is negative 12a. And on the right side of the equation, the coefficient of t cubed is 2. So what we do here is we set negative 12a equal to 2 and solve for a. We get negative 1/6. So then we take the coefficient of t squared, which is negative 12a minus 12b, and set that equal to the coefficient on the right side, which is 0, because there is no t squared term. We then plug in the a value that we found above, which was negative 1/6, and solve for b, which we find is 1/6. We do this for our other two values, and we find that c is equal to 1/9, and d is equal to negative 5/27. So we found values for all of our coefficients, and if we were to plug them all back into the original function, along with our guess for y particular, we would see that the whole system is satisfied. It all works out. The left side equals the right side. So we know our guess was correct. And so we can add this to our original homogeneous solution and get a general solution to the whole system. So we get our homogeneous solution, c1 e to the negative 2t plus c2 e to the 6t, added to our guess with the coefficients we found, which is 1/6t plus 1/6t cubed minus 1/6t squared plus 1/9 t minus 5/27. And that's our final solution. So there are obviously a few bit more complex scenarios that you can have when dealing with the method of undetermined coefficients. For example, what happens if I have multiple simple functions? What do I do? If I have, if my non-homogeneous term is an exponential term multiplied by a polynomial or something of that nature. What you do is you make a guess for each specific simple function, and you multiply your guesses together. So for example, if our non-homogeneous term g of t was equal to 3t times sine of 4t, we see that that's a polynomial times a trig function, sine of 4t. So what we do is we make our guess for our polynomial, which is going to, in this case, be a1 times t plus a naught, and then we multiply that guess by our guess for the trig term, which is b times sine of 4t plus c times cosine of 4t. We multiply these guesses together, simplify, take the derivative as usual, and solve for our unknown coefficients. That's what you do in a more complex situation. If you have any further questions or want to see further examples, please feel free to visit one of these two websites that have a lot of information and examples available to you, as well as things on related topics like method of characteristics and that sort of thing. Thank you.